right, so here we go. This is my last day. I'm gone here. So we've talked a little bit about enzymes in 3.1. We went to 3.2 and got a little deeper. Again, we talked about, remember, there's the active site. We've talked about, induced fit, substrates. Now we're going to look at, what role does the environment play on enzymes, right? So, you think about this. There are fish in the ocean that live near the bottom where the water is below freezing, but since the water is so high in salt, it won't freeze at that temperature. But they have enzymes that function in a low temperature. If you bring them up to where it would be warmer, the fish couldn't survive because their enzymes wouldn't work properly. And so we are like that. We function better when it's, like it is now, about 70 degrees. We're comfortable all the time. If you get too hot or too cold, then that would affect our enzymes and how fast they work and how well they work. But we want to, and for this one, we're going to look at how the environment is going to impact. Now, you got to remember, enzymes are proteins. And I'm telling you, we've been drilling this, that if a protein is not folded correctly, it will not work. When a protein is misfolded, that word denatured. So if, for example, if you ever watch an egg, I think we talked about this. If you fry an egg and you watch the egg white that's clear or kind of a yellowish, but when you put it in the heat, it turns white. That's because all of the proteins in the egg are going from being circular, they're straightening out. Okay, this is an irreversible process, we know. So it goes from clear to white and it will never go back. Now, keep that in mind. That's called denaturing. So if I were to say, what is it? A misfolded protein. Misfolded protein. Kind of a delicate balance. If you look at the picture there to the right, you see a normal protein. You could say this actually would be a very good model for albumin, which is the egg white protein. Normal protein, this is the way it's folded. Anything out, it no longer functions. But if you do a couple things for it that you need to know in AP, it will maybe straighten out or unfold, or maybe it'll fold in a different way and it becomes denatured. So this would be a normal. And if you think back, this could be the quaternary structure. Remember, there's the I can't think of the primary structure. Then you go to the secondary structure, tertiary structure, and then the quaternary. And then if you expose it to two things we're getting ready to talk about, this could happen here. Now, I think maybe I told you this was irreversible, but there are some instances where this is reversible. For example, guys necessarily wouldn't have to worry about this, but girls who curl their hair or straighten their hair with a hot iron, that doesn't last forever. But that heat will straighten out the proteins if, depending, or curl it however you want to do it. It's denaturing the proteins that make up the hair, but eventually it comes back. So that would be an example of it not being permanent. Okay, so two causes for denaturing. Now, if you add, obviously, heat, you could change that 3D nature of a protein, right? That will make it maybe fold up as like in an egg. Another one is a change in the pH, the power of hydrogen. So we're either going to look at how acidic or how basic it is. So those two things, mainly, those are the ones that you're going to have to worry about the most. But I want to look at, for now, I want to show you, you could actually, we'll look at both of these. You might want to, I'm not going to spend a lot of time on this. You can go back and look and copy these down. If this were temperature, every enzyme has a proper temperature. And so you can see as the temperature rises, here the enzyme is not functioning properly. But as it warms up, if this were the temperature going higher, there's going to be a point where that is where it is working at its maximum speed. Now you notice if you go hotter, then it will denature. Now here you don't see denature. So if it gets cold, maybe it could denature, it depends, but normally you won't have to worry about this in AP, but hotter it gets, the more it denatures. Okay, so that would be like temperature. So every enzyme has an opposite or an optimum where it's going to work the best. It's going to be really quick. You know, and it tends, think about it, heat tends to speed things up. And so even if it gets too hot, it then is going to affect it because it's denatured. It's changed that 3D shape. Next one, pH. Now, here the only thing that's different is that every enzyme has an optimum pH. You know, whether it's going to be too, we could say this would be acidic, this would be basic, but you notice if this was the optimum pH, if it falls below, it's going to denature it because, you know, even though these are on opposite ends of the pH scale, they're going to have very similar effects on a protein. And then again, if it gets too acidic, it's going to denature the protein. And you know, once it's denatured, it's not going to function well. So this is the optimum. Okay. I was here so I could answer some questions. Okay. Now, I'm going to ask you a question here. What's going to happen? Think about it. To the speed of the reaction. We did a lab last week with the paper dots, right? Using the paper dots, and we used hydrogen peroxide and yeast. And you saw what would happen as we started with maybe a concentration of the least solution that was watered down, so there wouldn't be a high concentration of enzyme or more enzyme in there. And then as we went up, you notice that the higher the enzyme concentration, the faster it goes. The higher the concentration of the enzyme, the faster it goes. And then on the opposite side, we started out with a 25% solution, and if the lower enzyme is going to go much slower. Okay? Now, if you look here on this, and again, you can go back and you can draw these since it's on the plan book, the Power School. Here's your rate of reaction, your enzyme concentration. Now you notice that it goes up and it's increasing, getting faster and faster and faster, but there's going to come a point where there's not, the substrate's going to limit it. One being that it's going to get crowded with substrate in there, and so this random motion, they're going to be banging into, the enzymes are going to be banging into the substrates that already have been broken up, or the product that's floating around, and it's going to even out that. And so, yeah, even though you have a concentration, high concentration enzyme, it's going to reach a certain speed, and then it's going to level off here. And then if you have a higher substrate concentration, okay, I'm back. That wasn't magic. I had this was less, and then I changed it to more. Now, think about it. If you have more substrate concentration, if you look, and if you do like an I square in your mind and you picture it and you see what's going on, you can see it looks very similar to the one up there. It's gonna speed up, speed up, speed up, speed up. And then pretty soon, all of your enzymes are gonna be active. And so all your active sites are gonna be used up. So it's going to increase the rate just to a certain point until I guess you would say that it's saturated. Okay. And remember, the more products you get, the more space it's taking up, and it will also slow it down. But in this case, more substrate, it's going to speed up until it reaches kind of a certain speed, and then it won't not get any faster there. Okay. And I think that is it.